The James Webb Space Telescope has finally made its first dark matter observations, and the results could lead us to new physics. They've questioned our understanding of dark matter and the large-scale structure formation of the universe. Dark matter is one of the most mysterious entities in the cosmos. Our best cosmological models show that 27% of the observable universe is made of dark matter. We can't see it, but its existence can be inferred because of its effect on surrounding baryonic matter. The true nature of dark matter is still one of the biggest mysteries in cosmology. The most successful cosmological model to date, the lambda cold dark matter, or the LCDM model, makes a critical prediction regarding dark matter. It says that cold dark matter played an important role to form the large-scale structures we observe today. So far, we did not have the technology to test this prediction, but the James Webb Space Telescope opened the windows to the first billion years and the last unexplored era in the history of the universe. The super early galaxies discovered by Webb in its early release science program provided an opportunity to test the predictions made by the LCDM model. And when astronomers did that, the results were completely unexpected. So what do these primordial galaxies discovered by Webb tell us? What did Webb find in its first dark matter observations? Finally, and most importantly, how can these results change the course of cosmology? The farthest galaxies discovered by Webb turned out to be completely different from what we had expected. There are three important things that you must know about these primordial galaxies. First, they have a high redshift of more than 11. This means that they are super early galaxies that must have formed within the first 500 million years after the Big Bang. Second, they have a large stellar mass of the order of 1 billion solar masses. That's puzzling because according to our models, galaxy formation takes about 1 billion years. We must be seeing clumps of proto-galaxies that are on their way to forming bigger galaxies. But instead, why are we seeing galaxies that are fully developed in the first few 100 million years of the Big Bang? Lastly, their star formation rate is way higher than what we expect for the early universe. So what is driving such high star formation activity in those galaxies? The LCDM model predicts how galaxy formation takes place, and according to it, cold dark matter has a vital role. Dark matter is hypothesized to be of different kinds. Astronomers propose cold, warm, and hot categories, and these types tell us how fast the dark matter particles can move. Hot dark matter is made of light particles, having speeds in the ultra-relativistic range. Cold dark matter is made up of heavy particles, having slow and negligible speeds. And warm dark matter falls in between, with matter particles that have intermediate mass and velocity. All three dark matter particles have a role in large-scale structures. Our models predict that hot dark matter moves so fast that it smooths out the structures. So it's not very useful in clumping the matter together for galaxy formation. On the other hand, cold dark matter is a clump builder as it moves slowly enough to merge matter and form gravitational wells, helping build galaxies. Finally, having intermediate properties, warm dark matter is also involved in galaxy formation. But as its particles are lighter than cold dark matter, the resulting structures are different. The cold dark matter lies at the heart of the most successful cosmological model, hence the name, the lambda cold dark matter model. But one question always remained unanswered. When galaxies were forming in the early universe, what type of dark matter was involved? Warm or cold? Unfortunately, we cannot find the difference in the local universe. So there's only one place this question can be answered: the first billion years of the universe. The highly redshifted galaxies that Webb saw provided an opportunity to understand the nature of dark matter and its role in large-scale structure formation. In their paper, The researchers first plotted star formation rate density against redshift. In galactic and extragalactic astronomy, the star formation rate is a significant number. It tells us how quickly stars form from gas and dust and is typically measured in solar masses per year. So the star formation density depicts the star formation rate per unit volume. The redshift is a measure of distance. The more the redshift, the farther a galaxy lies from us. When researchers plotted these parameters for Webb galaxies, they found that high redshift galaxies can only be explained by cold dark matter models. The warm dark matter models could not predict the formation of high redshift galaxies. Hence, they were ruled out, corresponding to the star formation rate of the observed galaxies. In addition, the researchers also compared the mass distribution of these galaxies and the density of the observed galaxies distributed across the UV luminosity across various warm and cold dark matter models. All these results indicate that it may still be cold dark matter involved in the galaxy formation in the faraway galaxies of high redshift. This means we were right about the nature of the dark matter involved in large-scale structure formation. But the LCDM model is now facing a serious problem. Although it may be right about the nature of the dark matter in high redshift galaxies, its predictions about the nature of those galaxies turned out to be the opposite. Properties such as high stellar mass, high star formation rate, and high absolute UV magnitude are not something the most successful cosmological model had predicted for these early galaxies. It may be because we still don't understand the role played by dark matter in the first few 100 million years of the universe. The contradiction of these results does not mean that the Big Bang didn't occur. That's because the Big Bang theory has plenty of observational evidence in its favor. Any new theory that is successful in explaining Webb's observations and the origin of the universe must also be in line with the predictions made by Big Bang that turned out to be true. They include the cosmic microwave background, the abundance of chemical elements, and the redshift of distant galaxies. What really needs attention is our understanding of dark matter. The data from the James Webb Space Telescope are pointing at a new scope for galaxy formation. This deviation from the prediction should be corrected, which may open doors to new possibilities of galaxy formation and correct our flaw in understanding gravity itself. Retaining the concept of dark matter is of utmost importance, because without dark matter, the foundation of our most successful standard model of cosmology will be in chaos. Therefore, a lot is riding on this debate around the nature of dark matter. If we can correct it and explain the nature of Webb's galaxies in the early universe, we can save the LCDM model that took decades to develop. Else, with time, we would have to establish a new theory, and we could be back to square one. This concludes the 36th episode of the Sunday Discovery series. So if you've enjoyed this video, make sure to like it, subscribe to our channel, and press the bell icon so that you don't miss any future videos of this series.